Sections on 8.4 improper integrals. So this is the only integration that we're going to do for this chapter 8. So the question is going to ask us to evaluate the improper integral or state that it diverges. So there are three cases. The first case is when f of x is continuous on a to infinity. And notice that a is a bracket because that's a real number and infinity has a parentheses. Then you're going to take the integration from a to infinity right there. And it's f of x is equal to, we have to write the limit again, so similar to what we just finished doing, from b approaching to infinity, and then from a to b right there. So the a right there is going to be our number that we have is usually going to become negative or a number that's smaller. Then b is going to be infinity up here. So a lot of times they like to write that in lieu of this infinity. So they don't put infinity up here, they'll put infinity down here of f of x. And then the second case is the opposite, when f of x is continuous on the negative infinity to b, then from negative infinity to b right there, you're going to have f of x dx is equal to the limit of a approaching to infinity, so down negative infinity, so that's down here. And then the b is going to be the same b that we talked about up here, so which is a number, and f of x. So the difference between these two right there is that this right here is going to be from infinity is positive on this one, so that's going to be up here, positive infinity, right? So that's why they put a b right there. And then this is going to be infinity's negative, so that's your a down here, okay? And then the third case is going to be when it's going from negative infinity to positive infinity. And so when you have this part right here, it's equal to negative infinity of c f of x dx plus the c to positive infinity f of x dx. Now c is any real number. So what we're saying that in this case, it's a graph that is possibly continuous, but then there is maybe a cusp or a corner. So where it's not differentiable. So if it's not differentiable, you have to cut it from negative infinity to the point that it's not differentiable, and then continue on from that point to positive infinity as well. So that's why this case is a little different right there. Okay. Now, if it actually is a continuous and differentiable from negative infinity to positive infinity, you do not need to separate this right here. All right. And then the other part we have to talk about is converging. So the definition of converging is that the limit is finite or has a value. So something like this, when you find the area, the integration under the curve, you're going to eventually approach to a number, like for example in this case we'll approach to 0. If it's 0, it's going to be converging. The opposite to that is when it diverges. So the limit fails to exist, so something like this where the graph goes on to positive infinity, and when you're trying to find the area underneath the curve, obviously there is no limits that will stop it because it'll shoot up to infinity and continues on right there. So that's the diverging, okay? So if it diverges, you don't have to complete the problem. You just say it diverges, you're good. If it converges, though, we do need to find the value for that, okay? So let's try the examples then. So the first example, that's going to look something like this. It says, again, the direction is evaluate the improper integral or state that it diverges. So we're going to have this kind of problem. And we're going to use everything that we know for integration. So again, when you approach an integration problem, you ask yourself, is it a simple integration? If it's not a simple integration, can I do a U sub? Can I do, if it's not a U sub, a tabular method? If I can't do a tabular method, then can I do by parts? If I can't do by parts, can I do by partial fraction? Okay? So in this case, let's go ahead and do this. So I'm going to take the integration of this right here. Now, this is a simple integration, right? Because the integration of 1 over x is going to give us then ln x. And then from there, it's going to be from 1 to infinity. And so from here, I'm going to substitute in ln of infinity, right? Minus ln of 1. And we know ln of 1 is equal to 0. So that's gone right there, is equal to 0. So ln of infinity, we learned from this last section, right, is same thing as a large number. So in this case, the answer is going to be just diverge because there is no limit to that. So we're going to find that to be a diverging problem. Okay? Now let's try example number 2. So example number 2, we're going to look at this problem and say, is it a simple integration? No, it's not a simple integration. Can I do a U sub? No, I can't do a U sub. I can't do tabular. It's probably going to be partial because of the denominator down here. So then we're going to have to separate this. So if I take the denominator and separate it, it's going to be something like x. If I could factor out an x, x minus 1, right? So then from there, I'm going to have to split it up. A over x plus b over x minus 1 is equal to 3. We cross multiply. You get ax minus a plus bx is equal to 3. So now we're going to separate this right here. So we have is ax plus bx is equal to 0 because there's no value right here. And then the other one is going to be negative a is equal to 3. So a must equal to negative 3. So if a is equal to negative 3, then on this right here, when we factor out the x's right there, you're going to find that b is equal to positive 3 then. Okay? So now we put it back together in that problem right there. So we have then is a is negative 3 over x. Now we take the integration, and we go back to the integration from 2 to infinity. So from 2 to infinity right there. And then we go to the other part, which is the b part, right? Which is this part right here. So that's going to be plus, and we're going to separate that from 2 to infinity, and then from 3 to x minus 1. And then let's put dx's, right? Kind of like the periods of our sentences right there. Okay? So then we know the integration of this right here. We'll just pull the negative 3 out. It's going to become ln of x, and then I have the limits from 2 to positive infinity, plus, and then do the same thing on this one, 3 ln of the absolute value of x minus 1, right? And then we have the limits from 2 to infinity, and then we substitute. So we have is negative 3 ln of infinity minus, and then because this is negative right there, it's going to become plus 3 ln of 2, right? Plus, and then we do this part right here. So it's 3 ln of infinity minus 1. And then we also have minus 3 ln of 2 minus 1, which is 1 right there. Okay? So let's see now. Let's see if I can simplify this. Now, the 3 ln of infinity minus 1, it's just going to be some large number right there. So since this right here is similar to this right here, we can just go ahead and say cancel these guys out right there. I know ln of 1 is equal to 0. 0 times anything is going to be gone right there, right? And so we just basically have is this part right here. So your final answer is then 3 ln of 2 right there. Okay? Now, the next part we're going to have is this part right here. I wanted to go from negative infinity to positive infinity so you can see that worked out. So same thing with this one right here. We're going to ask ourselves, can I do a u sub? Well, let's see. If this is your u right there, and I take the derivative of that, that's going to become negative 6x, right? So that's possibility that's going to cancel this out right here. So let's do a little u sub on the side then. So u is equal to negative 3x squared. Du is equal to negative 6 dx. Oops, x right there. So then it's 1 over negative 6x du is equal to dx. So we have then as the integration from negative infinity to positive infinity of x eu times the negative 1 over 6x du. So then the x's will cancel each other out. Beautiful. So we'll just pull the negative 1/6 in the front of the integration symbol right there. And then from there we're going to continue on from negative infinity to positive infinity eu, right, du. And we love the integration of eu because that's just basically eu. So it's going to be negative 1/6 eu, oops, eu. So then u we said was back here is negative 3x squared, so I'm going to substitute that back in from infinity to negative infinity right there. Okay, so now let's do the substitution part of it. So let's do that on the side right here. So then I have is negative 1/6 e to the negative 3 infinity squared minus, and then that'll be plus again because it's negative 1/6. So plus 1/6 e to the negative 3 negative infinity squared. Okay, so now this right here, because it is squared, it's going to become positive. So actually it's not going to change much for us. So it's going to become e to the negative 3 infinity squared, right? And then we have is plus 1 over 6 e to the negative 3 infinity as well, because this right here is positive. Negative times negative is positive right there. So it doesn't change the value right there. squared, right? So then from here we can see that they're pretty much exactly the same, so we're just going to cancel everything out, and then the final answer is then 0 right there. Okay, so this is pretty much the same as what we've been doing for integration previously in AB. The only difference is now we're going to substitute in infinities and also numbers into our limits, and then we're doing the same thing. We're either using a simple integration, we're going to use a U sub, partial fraction, any of the things that by parts, any of the things that we've already learned on the U subs, I'm sorry, for the integration. Okay, all right, try these problems now.